Hi there. This is Chapter 6, Part 2. There'll be two videos here. The first video is going to cover shapes and polarity, and then the second video will cover formulas. The first bit of notes here is just vocab. I'll let you read that on your own. One concept we are coming back to from a previous chapter, Chapter 4, is electronegativity. It's one of the trends we talked about in Chapter 4. And it's how much in an atom attracts an electron. And we'll come back to that in just a second. Covalent bonds can be either polar or non-polar, and this is a result of differing electronegativities. And you probably heard the word polar before, like polar bears, the North Pole, the South Pole. Basically, a polar bond is a bond that has a positive and negative side. Just kind of like the Earth has a north and south pole, or a magnet has a north and south pole. Bonds have poles also. It's different from magnetism. It's more of a charge thing, so it's a positive and a negative side. Polar covalent bonds are created when electrons are not evenly distributed, or they're not evenly shared. So one of the two atoms that are sharing the electrons has a greater electronegativity. And again, electronegativity is how much an atom attracts or how much it pulls on those shared electrons. So if one of the atoms has a higher electronegativity, it's going to pull those electrons towards it and kind of be an electron hog. Good example of that is if we look at a bond between carbon and fluorine. Normally we write a bond with a line, so a single bond. But in this case, I think it's helpful to think of it as those dots. So we have those two shared electrons between the carbon and the fluorine. And since fluorine has such a high electronegativity, it's much higher than carbon, what it does is it kind of hogs those electrons. So the electrons actually get kind of pulled over towards the fluorine. So you end up with something a little more like this. The fluorine is hogging those electrons. They're still sharing them, but the fluorine kind of pulls them closer to it because its electronegativity is higher. Now what that does is, since electrons are negative, it kind of makes this side of the bond negative, and if that side's negative, this side's positive. So hopefully that makes sense. That is a polar bond because one of the two atoms is pulling the shared electrons towards it, making that side of the bond negative. So this creates a polar bond, has a positive and negative side. Another vocab word here, a dipole is a molecule that has two poles, has a region of negative and a region of positive. Just a little vocab there. A non-covalent bond is when the electrons are evenly distributed. Example here is if we have two of the same element sharing electrons. So let's say we have a nitrogen and a nitrogen bond there. But again, I'm going to draw it with the dots. Well, we have two nitrogens here. Nitrogens have the same electronegativity. Any two atoms will have the same, any two identical atoms will have identical electronegativities. So it's like having a tug of war with your exact same twin that's exactly as strong as you. No one's going to win this tug of war here. They're both pulling on those electrons evenly, so they're evenly distributed. They're shared evenly. And since one side isn't pulling the negative electrons one way or the other, you don't get poles. You don't get a positive and negative side. So that's what we call a non-polar bond, is when those electrons are being shared evenly. There's no symbols or anything that we use for nonpolar. We just call it nonpolar. There are some symbols that we use for polar bonds to show the polarity of that bond. So if we have carbon and fluorine. Again, fluorine is the electron hog here. I particularly like the arrow with the plus sign symbol because the arrow points in the direction that the electrons are getting pulled. So since fluorine has a higher electronegativity, it's pulling the electrons towards it. So that's the way the arrow points. If I were to write this the other way, if I would have written it F over here and C, I would have drawn the arrow the other way, and the little plus sign shows the positive side. The other type of symbol you may see in books or you may use, I don't like it as much, but you'll see it in books, is using the lowercase delta, which is a lowercase d in the Greek alphabet. It kind of looks like a funky 8 that you don't quite finish. And the fluorine, since it pulls the electrons towards it, it's negative, because electrons are negative, which means the other side is positive. Either one is fine. You can use the delta, the little 8 thing here, a little half-finished 8, or the arrow. Either one is fine. One thing you will want to do is, one thing you need to memorize are the diatomic molecules. There are 7 molecules, or 7 elements, sorry, on the periodic table that will form diatomic molecules when they're alone. So here are the 7. I'll teach you a little trick to remembering them. One of the 7 is oxygen. So when we say we breathe oxygen, we're not breathing individual oxygen atoms, because oxygen, being one of our 7 diatomic molecules, oxygen is never going to be alone. It will always go out and find another oxygen and pair up with it and become a diatomic molecule. Di meaning 2, we know that prefix from earlier in the chapter, and diatomic meaning 2 atoms. So it's a molecule made up of 2 atoms. So again, all these, they'll never be alone. What they'll do is they'll find another one of themselves and they'll pair up and become this diatomic molecule. Now the trick to remembering is just remember the number 7. If you start at number 7 and make a 7 shape, so you go NOFCLBRI, that makes our 7 shape that starts at number 7. That only gives us 6. Just remember H is also one of the diatomics, hydrogen. So start at 7, make a 7, and then hydrogen. That's a little trick to remembering the 7. You will want to remember those. We'll use those more in future chapters, but I wanted to introduce them now. So the next thing I want to talk about is molecular shapes. So we've been drawing these pictures, these Lewis structures, and we haven't really worried about the shape too much. We've just been drawing the pictures of them and saying there's a Lewis structure of CH4 or whatever. Now we're going to we have names for the different shapes of molecules. And the molecular shape all depends on this concept or this theory called VSEPR, valence shell electron pair repulsion theory. So valence shell means the outer ring of the atom. So valence electrons. And if you remember, when we drew those dots, those dots represented electrons in the outer ring. Now, if I do something like neon, if you remember, we go around once, and then you started pairing them up. Electrons like to pair up. They don't prefer to be alone. So, electron pair just meaning a pair of electrons. Now, repulsion. Repulsion means repel. So if I draw CH4. I've done this enough. I know that it adds up to 8. And the final Lewis structure looks something like that. The reason I didn't draw it like this is because, remember these lines? The line represents 2 electrons that are being shared. Well, Vesepper says these electrons repel each other based on the fact, or the rule that we use in chemistry, opposites attract and like charges repel. Electrons being all like charges, they repel. So this pair of electrons wants to be farther away, as far away from this pair of electrons as it can be, and it goes for all of them. So what it does is it determines the shape of the molecule. This whole fact that the electrons repel each other. So Vesepper explains the shape of the molecules. It's based on the idea that electron pairs repel each other and trying to get as far as possible. Unshared pairs, like if I draw NH3, the nitrogen has an unshared pair. So the nitrogen here has 2 electrons that are what we call unshared pairs, or lone pairs. Now these have bigger repelling powers than shared electrons. The molecular shape is important. One of the reasons water is such a useful and necessary molecule for life and all that stuff has to do with its shape. Its shape determines a lot of its chemical and physical properties. There are 5 shapes that we're going to study. Linear, bent, trigonal planar, tetrahedral, triangular, pyramidal are the 5 that we'll study. There are more, but these are the ones we'll study. And just like we can have polar and nonpolar bonds, we can also have polar and nonpolar molecules. So the overall molecule can be polar or nonpolar. Now, there's a fair amount of stuff here that we just covered. You will get kind of a cheat sheet or another handout. And this is that handout. You will have a link on the Moodle site, so you can print this out. I'll put it up as a PDF, and you can print this out. And we will use this handout that shows the different shapes on one of those days in class that we meet. So you'll get to use this. Maybe I'll move this over. I'm going to pause it for a second. Okay, there you go. Now you can see the entire handout here. The 5 different shapes: linear, trigonal, planar, bent, tetrahedral, trigonal, pyramidal, and the other bent. There's 2 different versions of bent. So we will get to that in class. So this is pretty much it for this video. The next video will cover formulas, and you will have a practice quiz based on the formulas stuff that we're about to cover. Thanks.